start the first lecture. So I hope I have already shared that. So this PPT is visible.
Yes, sir, it's visible.
Okay, okay. Thank you very much. So just I am turning off the video. Maybe otherwise someone will not able to see the PPT properly.
Sure, sure.
Okay, okay, thank you very much. So let us start. Uh, so I think we all have some basic idea from 10 plus 2. Whenever we have, like, I think this example we all have already learned. Whenever we have two wire or we have single wire and current is flowing in that, then one magnetic field arises surrounding of the wire. So what happens? Suppose if you have two wire and the current is flowing in same direction, then we used to feel that they attract to each other. Similarly, if current is flow in opposite direction, they repel to each other. So these are the few things whatever we are knowing from long time. Similarly, if you talk about the magnet, so, if you we have like very good history about that. So, a magnet is a material or object that produce a magnetic field, and if you take that magnet very close to the iron, then it's attract the iron. This is the basic property of the magnet. So now question is arises how magnetic property come in any material. How we can understand how some material attracts some other material, and how material repel to other material. How some material so the non-magnetic behavior. So these all we can understand on the atomic level easily. So before that, like, okay, this is here, like we have a small history about the origin of the this magnet. So basically, it started very long back, 3000 BC, when people have made this compass for the navigation. After that, they found this iron oxide, which are naturally attract the iron. So similarly, like step by step, people move in advanced stage, and they found several other unique property in the this magnetic material. So if you look about the application, so in our surroundings, we are all the places, several places we are using this magnetic behavior, magnetic property, something like that. In GPS tracking system, we are using this magnetic concept. In credit card, we are using this magnet. In hard disk, we are also using the magnet, and even this electric power generation we are using this magnetic concept from the long time. So now question is that whenever we have any material, how this magnetic property come within that material. So let's understand on very basic level. Suppose uh, suppose we have electron mass m and charge of electron is minus e, which one is moving with velocity of magnitude v in a circular Bohr orbit of radius r, as you can see in this here. So when electron move in the orbit, then what happens? Definitely it generates the current. That current equal to, we can say, charge divided by the time taken by to complete the electron to this orbit. So of course we can say this time period, time taken by the electron to complete this path, that one is 2 pi r by v. Okay, so then we can easily calculate I equal to ev by 2 pi r. 2 pi r is the radius of this Bohr. This is the Bohr uh, 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 the path of this orbit. So then we can easily calculate this dipole magnetic movement due to this movement of the electron in the orbit. Uh, you can represent with the mu L. That one is equal to current multiplied by the area. And if we can put this current here, EV by 2 pi r and multiplied by area means pi r square, radius is r, so we can easily say this is the pi r square. So it means mu L equal to EVR by 2. That's what we can say. Okay, so if you look here, because electron is moving in the orbit, so this one is also generating the angular momentum, which one is just opposite to this dipole magnetic moment. So this angular momentum we can easily calculate equal to basically mvr. And if we can divide this mu L by L, then we will get almost proportional to E by 2m. Mu L by L equal to E by 2m. And because this one is just proportionality constant, so definitely we will get one constant. When we are going to equate this equation, then we will get mu L equal to minus GL E by 2m with vector L. Here minus sign basically indicating that this generated dipole magnetic moment is exactly opposite to this orbital angular momentum. So and mu L, because this gyrometric ratio GL is basically for this orbital motion, it's always equal to 1. So specifically we will get this equation whenever electron is moving circular orbit in Bohr radius. Here, because this angular momentum is quantized, so the quantized behavior, and that one have relation with the orbital quantum number L, H cross under root LL plus 1. So it means we can replace this vector L with this orbital quantum number, which we are familiar, like principal quantum number, orbital quantum number, magnetic quantum number, spin quantum number. These four quantum number exist for any electron. So here, this Bohr, like orbital dipole magnetic moment, that will equal to EH by 4 pi m under root L plus 1, where L is the basically orbital quantum number. So we can easily calculate how much dipole magnetic moment generated when one electron move in the circular Bohr radius. So that one, of course, equal to, we used to write mu L equal to under root L plus 1 mu P. Mu P is nothing, that one is equal to EH by 4 pi m. And this one is also known as Bohr magnetron. And if we put the value of electron, Planck constant, and mass of the electron, then we will get this value equal to 9.27 cross 10 power minus 24 ampere meter square. Okay, so this dipole magnetic moment basically arising due to motion of the electron in the orbit. Now next, because the electron is having two type motion. One motion, basically electron is moving in the orbit. Second motion is happening. This electron is also orbiting about their own axis. So this rotation of electron about their own axis, that one have two possibility. Maybe have electron up spin or down spin. We have two possibility. So using the similar concept, when you can like analyze that, then you will find one spin magnetic moment is generating due to rotation of the spin about their own axis. That one is okay. You can easily write US equal to GSE by 2m S. Okay, so here because electron have two possibility, maybe electron is upward or downward. That's why here like you have a GS E by 2ms. and GS is basically excellently observed that that one is the 2. And S is nothing, that one is equal to S plus 1. This is the spin quantum number. That one have two possibility, plus minus half. And if we can put this value of S here, then we will get this small s, that one is equal to under root 3 by h cross, or mu s, that one is equal to root 3 eh by 4 pi, or mu s equal to root 3 by mu b. So if you look like these two, because we are getting the dipole magnetic moment on two way. One, when electron is moving in the Bohr radius. Second, when electron is also orbiting about their own axis. So, but if you compare these two, then you will find this dipole magnetic moment which coming from this motion of the electron about their own axis, that one is always higher than the orbital motion. So now next, because here we have two type motion. One is orbital motion. Second one is the spin motion, orbiting of the electron about their own axis. So basically, we have two vector. One is this coming due to this orbital motion of the electron, that one is vector L. Second one is the spin vector, which one is coming due to orbiting of the electron about their own axis. So we have vector L and vector S. So now just move next, because when now what we are doing, we are going to apply the magnetic field. It we have discussed without applying the magnetic field. Now when we apply the magnetic field on that system where electron is moving in the Bohr radius, then what happens? So normally, after applying the magnetic field, this spin or this electron will start, this spin will start to align in direction of magnetic field. Just assume if this angle is L, if this angle is L with respect to applied magnetic field along the g-axis, then okay, we can easily write that a line component, that Lz equal to L cos theta, and cos theta equal to Lz by L. Here L is nothing, that one this one is the orbital magnetic moment, that L equal to h cross under root L of L plus 1. This is the orbital quantum number. And Lz, that one is equal to ml h by 2 pi. ml is the basically magnetic quantum number. And value of ml always lie between plus L to minus L. Basically, you will get 2L plus 1 state. And L, of course, suppose if you have idea about the principal quantum number, then value of L, that one is equal to 0 to n minus 1. So on that way, we can easily calculate this cos theta or value of theta, just putting the value of Lz and L, because we are getting L equal to under root L plus 1 h cross, and Lz that will equal to ml h cross. So just if you divide these two, we can easily get the cos theta equal ml upon L plus 1. Here ml value always, because if L is known, then definitely we can calculate the value of ml. That you will get for 1L, you will get 2L plus 1 state for the ml. So that's why we are used to say these are the discrete orientation give rise the space quantization. So space quantization is coming due to this ml. Now just try to take one example here. If L equal to n, so definitely we can say ml equal to 1 0 minus 1. And Lz, okay, we can easily Lz equal to basically Lz, what you have, Lz equal to ml h upon 2 pi. So just try to put value of ml 1 0 minus 1, then you will get uh, h cross 0 minus h cross, or h by 2, h by 2 pi basically is h cross. So we can easily calculate the different orientation cos theta equal to ml upon under root L plus 1. So cos theta equal to 1 upon root 2. If you just calculate yourself, then you will find cos theta equal to 1 upon root 2. 1 upon root 2 is equivalent to 45 degree. Cos 0 is nothing, that is equal to 90 degree. and cos theta equal to minus 1 by 2, that one nothing equal to 135 degree. So basically, if you look here for these different ml value, you have different states. So that's why it's not known as space quantizations for the dipole magnetic moment. So now, similarly, we can also see the quantization effect in the spinning of the electron, because as we know that this spin quantum number s equal to h cross ss plus 1. Here s is nothing, that one s value is always half, plus minus half, and if we can choose s equal to half, so basically we will get the 2ms value, that one is plus minus half, and sz is nothing, that one equal to ms by ms h cross, or ms h by 2 pi. So on that way, here we will get only two states, not more than two. We will get only two states. So now once we have this orbital quantum number, and we have magnetic this magnetic quantum number, then our spin quantum number, then we have to move next, because we have to look resultant vector, because resultant vector, that one is basically people say total angular momentum, that j equal to L plus R S or L minus H, depending types of condition. So, if as you know that L equal to L plus 1 H cross, and Lz, that one is coming ml H upon 2 pi z component. Similarly, for the S, that one is SS plus 1 H cross, and Sz equal to ms H upon 2 pi. Then we can calculate the resultant component, that J equal to L plus S, and j value, that one is equal to nothing, that is equal to jj plus 1 h cross, and zz mj h upon 2 pi. So through the vector diagram, we can understand whenever we have this orbital vector. So just try to look, this one is coming due to motion of the electron in this orbit, and when we have the same times electron is also spinning about their own axis, so we have this s vector. So resultant vector basically is the sum of these two. Of course, like j equal to L plus s or L minus s, depending on magnitude of L and s. So how this one is behaving, so basically it's going to depend on these two. And the same times, when we are applying the magnetic field, then what happening, this total uh, vector of j, total angular momentum, is going to traces around the with going to presses around the magnetic field with the Larmor frequency. So now question is that when you will get j equal to L minus s or j equal to L plus s, basically depending condition, when j is greater than L, so definitely it means we have j equal to L minus s, and if j value is less than L, so we used to we have to use j equal to L plus s. So these two conditions we can utilize for calculating total angular momentum due to motion of the electron in the Bohr radius, and same times spinning of the electron about their own axis. So now we got the idea. Whenever electron is moving in the Bohr orbit, then it's generating two type dipole magnetic moment. One is due to motion of the electron in the Bohr radius. That one is known as orbital dipole magnetic moment. Second one is the rotation of the spin about their own axis. That one is the dipole spin dipole magnetic. So basically we have two types of dipole magnetic moment. It's arising due to motion of the electron in Bohr radius. So because whenever we're going to move in the material, so definitely we have n number, like n numbers of electron, or depending how many unpaired spins we have, in our orbitals. So it depending on that basically. So if we have n numbers of electrons, so you can going to multiply with the n numbers, then you can calculate total magnetic moment within that material. So now, of course, on the basis of this, so because this dipole moment orientation or spin on the base of spin orientation, we have different type this magnetic material. So, of course, like one is diamagnetic material, second one is the paramagnetic material, third one is the ferromagnetic, antiferro, and ferro. These all five different type material, all is depending how dipole these moments are aligned after applying the magnetic field. So now try to look the first one, diamagnetic material. So we will go one by one to understand what is the diamagnetic material, what is the paramagnetic material, what is the ferromagnetic material, and what is the antiferro and the ferro. So if we look this diamagnetic material are the magnetic material having the dipoles oriented in such a way that the resulting dipole moment is zero. The external magnetic field changes the rotation of individual dipoles. This produces an induced magnetic moment and it opposes the applied magnetic field. This weak effect, this is the weak effect and decreases the magnetic induction present in the material. This effect is known as the diamagnetism. And if we talk about the property of the diamagnetic material, so if you look here, this is the normal state. So we these all dipoles are oriented in one direction. When magnetic field is applied, just try to look. So here in this material, magnetic field generated on such a way, it opposes the external magnetic field. So basically, if you look here, these magnetic lines are not going to pass this diamagnetic material. That's what happening through the diagram. You can easily understand. So simplest example, okay, if you look the superconductor, it's known as the well-known diamagnetic material. So here, if you look in terms of the property, so diamagnetic material basically repel the magnetic line of forces. So as you can see through this diagram. Second, of course, you can say there is no permanent dipole moment. Therefore, the magnetic effect are very small. And magnetic stability is negative and is independent of temperature and applied magnetic strength. Susceptibility means what? Susceptibility means uh, magnetic moment are divided by the applied magnetic field. Magnetic moment divided by applied magnetic field. So basically known as the susceptibility. So magnetic susceptibility always you will get the negative in this diamagnetic material, and of course this one is independent of temperature and applied magnetic field strength. Magnetic permeability is less than 1. Whenever we have diamagnetic material, this magnetic permeability always you will get less than 1. So just this is the basic property which you will get in the diamagnetic material. Now try to move next about the paramagnetic material. So in paramagnetic material, dipoles are randomly oriented. As you can see this diagram, the dipoles are randomly oriented in such a way that resultant dipole moment is not equal to zero. If you try to add all these dipoles together in magnitude, so the sum you will never get the zero. So there is a small amount of resultant magnetic moment in each atom even in absence of magnetic field. That's what happening. So, and when an external magnetic field is applied, then magnetic movements of individual atom oriented itself along the direction of applied magnetic field and the material is magnetized. So that's what happened in the paramagnetic material. And if we look the property, Okay, so here time is limited, so I will not going through the derivation. So directly just I am explaining few property. So parametric material basically have this property. First one, parametric material attract the magnetic line of forces, as you can see in the diagram. They passes permanent dipole magnetic moment. Of course, they have like some amount of dipole moment is always there even without applying the magnetic field. And we can easily calculate susceptibility using this formula C equal to chi equal to C upon T minus theta. Here C is the basically Curie constant, T is the absolute temperature, and theta is the Curie temperature. So, and magnetic susceptibility is always greater than 1. And when the temperature is less than the Curie temperature, the parametric material changes as a diamagnetic material. So, basically, it's temperature dependent. Okay, so next, if you move towards the ferromagnetic material, so just try to look this diagram here. So if you look here, all dipoles are aligned in one direction. All dipoles are aligned in one direction. So such type material basically they have finite value of magnetization even without applying the magnetic field. So because here like this dipole moment all are in one direction, so you can understand like if you take the sum, magnitude is very high, so that's why, so always we have some magnetic moment even without applying the magnetic field. And if magnetic field is applied, then of course it's attract the magnetic lines very strongly. So here if you look here, this uh, inside this dipole magnetic moment is always greater than V. So maximum magnetic lines are going to pass through the this ferromagnetic material through the dipoles. So, as example wise, you can see that this iron, cobalt, nickel, these they have this property. Even if you remember, iron oxide, this one is well known magnetic material which attract the iron metals directly. So it's indicating that even without applying the magnetic field, they have very large magnetic moment or large creating large magnetic field. Which one is attracting other magnetic material. So if you look property, basically, okay, you can say all the dipoles are aligned parallel to each other due to magnetic interaction between two dipoles. They exhibit magnetization in the absence of field, as I've already explained. So even without applying the magnetic fields, they have some magnetic fields. That magnetic field is also known as molecular magnetic field. So property of ferromagnetic material also called the spontaneous magnetization. Spontaneous magnetization means even without applying magnetic field, materials show the this uh, they have very strong magnetic field inside the material. So such type material also exhibit the hysteresis curve. Hysteresis curve means if you are going to plot MH curve, magnetization versus field curve, in increasing field and decreasing field, you will always find the hysteresis within that. Of course, like if you heat the material above the Curie temperature, okay, so they will lose the magnetic properties because this all dipole moment will align randomly. So basically, this one is a temperature dependent property. Even only below the Curie temperature. Curie temperature means some temperature below that materials show the ferromagnetic behavior. Above that materials show the paramagnetic behavior. So so here, okay, we can easily calculate the susceptibility curve, that susceptibility using this formula chi equal to C upon T minus theta, where T is greater than theta, so it means material show the uh, uh, paramagnetic behavior. Below that, it show the ferromagnetic behavior. Okay, so next one, of course, like so next one, the antiferrometric material. So once you got the idea about ferrometric material, so what had we had in ferrometric material? All dipoles are aligned in one direction. But now if you look here in antiferrometric material, basically all dipoles are not aligned in one direction. Some dipoles align in opposite direction. And if you take the sum of the dipole magnetic moments, basically we will get some amount of magnetic moment. Uh, okay, so in basically like in this antiferromagnetic material, so magnetic interaction between any two dipoles align themselves anti-parallel to each other, as you can see through this diagram. They are anti-parallel, not in the parallel. So all the dipoles are equal in the magnitude. Therefore, resultant magnetization normally you will get the G. So normally, if you have antiferrometric material, they are not able to attract other like iron or other materials so easily. Okay, so that's why like here example wise you can see magnesium oxide, chromium oxide, or ferrous oxide. So if we look the property of the antiferromagnetic material, so dipoles are not aligned themselves antiparallel to each other. Therefore, resultant magnetization is zero. That's what is going to happen in the antiferromagnetic material always. And once if you apply the magnetic field, then what happens? So whatever spins, they are not aligned direction of magnetic field, they start to reorientate in direction of magnetic field. Then slowly, what you will find, if you measure the magnetization, then you will find slowly magnetic moment will increases after increasing the magnetic field. So it means these alignments of dipoles start to align in direction of magnetic field after applying the external magnetic field. So definitely its magnetization is fully depending on the external magnetic field. So, similar to ferromagnetic material, this antiferromagnetic material also lose the property above the Neel temperature. Okay, below the Neel temperature, of course, they will show the antiferrometric behavior. But if you go above the Neel temperature, this material also lose the antiferrometric property. Okay, so just assume like if you have susceptibility data, susceptibility means magnetization divided by chi equal to magnetization divided by applied magnetic field, external magnetic field. And if you take inverse of that and plot with respect to temperature, then what you will get? You will get the straight line on this way in ferrometric material. In paramagnetic material, you will get a straight line, which one is going to pass through the zero. In antiferrometric material, you will get the almost like such type slope. And if you extend this slope other side, they are going to cut on this x-axis somewhere on the negative side. So this is the basic difference fundamentally when we are going to compare ferro, anti-ferro or parametric material using the uh, susceptibility data. So just if you have susceptibility data, just take the inverse of that with respect to plot with respect to temperature. So through this, you can easily get the idea your material is ferro, anti-ferro or high parametric property. Okay, so after explaining this basic property, here I am going to discuss one application, which one is very interesting, application of the magnetic material. So this application is known as the, see, whenever you have any magnetic material, you can use the magnetic material for different application. Similarly, we have also used the material for making the magnetic refrigerator. Then definitely we will ask how we can make the magnetic refrigerator. People have already designed and developed the magnetic refrigerator and that one is working well. So now, what is the concept? How this magnetic material is magnetic vegetation is based on this magnetic material. So try to you will understand through this diagram. So just assume that whenever we have any magnetic material, magnetic and when magnetic field is zero and T is almost equal to Tc. Okay, so so it means that all spins are randomly oriented. So definitely this time material have some temperature T1 and entropy S1 because spins are random. So definitely we can say that entropy is very large. Now, if you apply the magnetic field, then what happened? All spin, all spin or dipole moment try to align in direction of magnetic field. So what happened? Entropy will reduce. So when H equal to 0, all spins are randomly oriented, you can say, or all dipoles are randomly oriented. Whenever magnetic field is applied, so these spins are aligned in direction of magnetic field. This is the basically property of the magnetic material. So basically here entropy is reducing after applying the magnetic field. Now, if we remove this magnetic field in presence of adiabatic region. So try to, what is the sense of adiabatic region? Adiabatic region means we are closing this magnetic material in such an environment. So it's not going to take any amount of heat from outside or not going to release any amount of heat in the universe. So basically, whatever heat that material, whatever energy that material have, that going to exist with that material. So it means total energy of system is always constant. So if we remove this magnetic field in presence of adiabatic region, then what happens? So again, this all spin will start to move in random direction. But system, uh, we have very close system, adiabatic system. So definitely, so some process is going to happen. Some process is going to happen. So that process, through that process, we will find change in the temperature. So that because we have adiabatic region, we are finding change in temperature, then that change in temperature is known as adiabatic temperature change for the adiabatic process. So now question is that how this temperature change is happening in this magnetic material after removing the magnetic field in adiabatic region. Just try to look here. If we have any material, so total entropy of any magnetic material have three components. One is electronic component, second photonic component, and third magnetic component. Basically, it's coming due to these spins. These spins. Because whenever we have adiabatic region, okay, whenever we have adiabatic region, then definitely uh, uh, energy is going to exchange, entropy is going to exchange between Sm to Se. Reason is that Se is directly proportional to temperature. Okay, so so it means whenever this spins are will go in random direction, so definitely this entropy will start to change or start to change, or we will find change in the energy. So that one going to compensate with the electronic part. So this SC is directly proportional to temperature. That's why we are used to see change in the temperature. So such type process change in temperature is coming when we are removing the magnetic field of any magnetic material in adiabatic region. So using this concept, people have successfully designed the magnetic refrigerator. Of course, like we can measure this entropy two-way. One, of course, direct measurement. Second, using the indirect measurement. Okay, so direct measurements basically known as the calorimetric technique. And indirect measurement, of course, you can measure using the existing techniques, whatever we have through the PPMS or BSM or squid. So if we have squid or PPMS, we can easily measure the heat capacity. And if we have heat capacity, the C by T integrate with respect to dt, then we can easily calculate the entropy. So this is the one curve we are showing whenever magnetic field is H1, and this one when magnetic field is H2, where H2 is greater than H1. As I have already discussed, when we are going to increase the magnetic field, then the spins are going to align. So definitely entropy will reduce. So just using the two heat capacity in presence of magnetic field and in absence of magnetic field, we can easily calculate the change in entropy in the magnetic material. Same time, if we keep this entropy fixed and measure the temperature this point to this point on same curve, then we can easily find the change in the temperature. It's known as adiabatic temperature change in the magnetic material. So, of course, if you have the magnetization data, then you can also calculate the change in entropy using this equation. But measure change in temperature using the using the MH isotherms. MH isotherm means you have different magnetization data on different temperature up to Tc. So, so now question is that uh, whenever anyone is interested to make the make this magnetic capacitor, so how they will decide which material is good or bad. So here just I am explaining. Whenever you are going to decide, you are interested to make magnetic capacitor in your lab, then just try to look these points. First point is that uh, people think like if the change in isothermal is large, then of course like material is good. So change when you will get change in entropy is large whenever first derivative of magnetization with temperature is large. Such type change you will get whenever you have first order transition in your magnetic material. Then one get. Second, large change in the adiabatic temperature. So, if you look like delta T adiabatic temperature is proportional to T divided by Cp and multiplied by delta Sm. So, if any material where numbers of atoms is very large, again it's going to affect the adiabatic temperature change. So, during choosing the materials, you have to take care of that point also. And third point is large refrigerating cooling power. So basically, you will get by using the change in isothermal change maxima peak multiplied by del T full width half maxima of that change in isothermal change. So again, if you have a first order transition or multiple magnetic transition in any magnetic material, then you can get large refrigerating cooling power. Third, and a very important point, if magnetic material is soft, because whenever you have the material, so you have two possibility. You have hard magnet or soft magnet. Hard magnet means when you are going to measure the MH curve, MH loop, then you will get the large hysteresis. Okay, and if you have some material where this hysteresis is very very small, then such type material is basically known as the magnetically soft material. And of course, when you are going to choose the material, you have to look the material cost also. Okay, so just here I am showing like one data. So just assume like this is the one material is known as LAFE air. Here I am showing the magnetization. Magnetization means magnetization versus temperature curve. Okay, so just try to look uh, this curve. So here we have this MT data or magnetization versus temperature data on different magnetic field. So if you look what happening, just see how we can explain how we are able to understand material is ferromagnetic or antiferro or hairy. So we can get the idea using these data also. So just try to look whenever field is small. So try to look initially coming magnetization changing some types here, then again change going up, then sudden change, then almost constant. With increasing the magnetic field, then try to look here, then again you have jump, then again almost peaks. If you look like here, we have one more peak also. So here basically we have three transition. If you look, one transition is here, one transition is here, one transition is here. So because using this data, we can easily understand here because if you look like this temperature data, here this change in the magnetization with increasing the magnetic field, almost no change in the this TC, T ordering. And then if you move from here to here, if you say this is the ordering temperature T2, then definitely we have change. Similarly, if you did this is also decreasing. So basically what happening here, like this T1 is known as basically anti-ferro to ferro, because if you say you have sudden jump, why sudden jump? Because some spins which are oppositely aligned, and after increasing the magnetic field, they are aligning direction of magnetic field. Okay, so once they are coming on this direction, material have another transition from this this ferromagnetic to a canted matlab anti-ferromagnetic transition. So that's why canted means like some spins like if you look this material, so iron have two position, two type irons are exist there. So these two iron itself have competition, spins iron they have competition to each other. So spins are canted. So that's why it's affected in this transition also. So similarly, like if you look here, we have another material GD5, G2SI2. Here, if you look like even if you change the magnetic field, it's not going to affect a lot. But if you look here, and hysteresis is also very small in increasing and decreasing order. So this material have only one transition. That one is the ferromagnetic, and above that, this opposed like you can say parameter. So on that way, we can say that if we have any magnetic material, then these materials are basically it depending on how dipole moments are aligned in any material. So that one is basically deciding you have ferro, antiferro, para, or ferry means if you remember like antiferromagnetic material, antiferro some spins are aligned in one direction, some are opposite, but magnitude are same. But if you look the ferrimagnetic, so these oppositely aligned is dipoles magnitude are not exactly same. They have different magnitude. This is the major difference in ferri and antiferromagnetic material. So I think now I am stopping here.
Yes, sir. We can stop for 5 to 7 minutes here,
Yes.
and then we can come back again.
Okay. Okay.
Okay, fine. We'll have this break of about 5 minutes now.
Okay. Thank you. Okay, so we may start.
Yes, sir, we can start.
Okay, thank you.
एक
Okay, so PPT is visible.
Yes, sir, it's visible.
Okay, okay, thank you. So I think let's start and discuss about the quantum material. So quantum materials, basically, if we talk about the quantum materials, so quantum materials are the substance that exhibit unusual property at the quantum level, often different from their microscopic behavior. These materials are of great interest due to their potential application in various technological fields, including electronics, computing, and energy production. So, quantum material itself like very broad topic. So here I am going to choose one specific direction as mentioned by Manoj, uh, magnetism in the quantum materials. So specifically here I am going to discuss toward the two-dimensional material. Okay, so this is just like a plan of discussion. Of course, I will discuss uh, some uh, history about the quantum materials, specifically toward the two-dimensional material. So basics of the quantum materials. So here basically I am going to talk about the uh, origin, the origin of the Hall effect, quantum Hall effect, and basically physics behind that. In presence of magnetic field, in absence of magnetic field, how its behavior. So I'm going to explain those all. And of course, like if time permit, then I will show you some of the my experimental results also. So whenever we are talking about the quantum materials, so quantum material origin specifically in two-dimensional material is very interesting. So if you remember the past, so this discovery occurs in night of 4th and the 5th Feb in 1980, uh, around 2 a.m. in the early morning. And name of discover is Professor Kitchi. And this discovery is basically known as the quantum Hall effect. And Professor Kitchi got the Nobel Prize in 1985. So now question is that what he was doing, why and what he was doing, and he got the Nobel Prize. So basically, he was working with two engineers. Name is Troda and Pepper. Uh, Basically, these two engineers they are used to prepare the high quality film of gallium arsenic, aluminum gallium arsenic heterostructures. And basically, they use those materials for preparing the field effect transistor. So, and they are used because whenever people prepare the material, they are used to perform the Hall effect measurement to get the idea about high mobility of the mobility in that material. Then only you are able to make the good device. So, major aim was to make the very clean system where they used to get very high mobility. So when Professor Kitchin was doing the experiment, as I already discussed, on 4th and the 5th, in 1918, 2 a.m. night, early in the morning. So he got the very interesting result. I will show you those interesting results later. So only this I am explaining it, they got very interesting result. So so on that way, if you this origin of the two-dimensional materials is started with very unique property that one is known as the quantum Hall effect. Quantum Hall effect you will get specifically in two-dimensional material when temperature is very low and magnetic field is very high. So, so you will get that effect. Of course, after this discovery, Then people got another discovery, that was fractional quantum Hall effect. Uh, then people again, these three scientists got the Nobel Prize. Then pure two-dimensional materials, because this gallium arsenic, aluminum gallium arsenic is man-made device, man-made material. But graphene is well-known two-dimensional material, which one is exists in the nature. So this Andre Game and Novetsko got the Nobel Prize in 2010. After that, again, like topological quantum material. This one is the extended version of quantum material. Quantum Hall effect, basically, you will see the effect in presence of very high magnetic field, but topological quantum effect, uh, people used to see in absence of magnetic field also. Reason is very interesting because these two-dimensional materials show the very interesting properties, something like that quantum confinement, enhance the many electron interaction, reduce the dimensionality, symmetry effect, several novel property and phenomena, several like very good optical electronic property, energy, you can use material in energy generation. So there's several interesting property people have already got that. So now question is that why we are learning this quantum material, specifically two-dimensional material? What is the reason behind it? So through this slide, we can easily understand that. So if you remember our current electronic device, like if you diode, all are based on diode, transistor, field effect transistor, and silicon-based technology. So basically, here electrons move the randomly. If you have any device, basically electron move the randomly. After applying some biasing, of course they start to move in certain direction. So then what happened? Because electron move randomly, so causes like a lot of scattering to each other. So a lot of heat loss. So if even if you remember with your laptop or mobiles, if you use very long time, then devices basically heat up. Whenever some devices heat up, they of course like lifetime of those devices reduce. But whenever we have two-dimensional material, specifically if we talk about a topological quantum material, so we can understand it this way. So these materials are like this. These vehicles are moving, both direction vehicles are moving in single lane road, causes huge traffic jam. And if you convert the highway, now we have highway, freeway, where one direction vehicle move in one direction, other direction vehicle move in other direction. So so no traffic jam. So at least so exact similar property we are used to get in the two-dimensional material, especially topological quantum material. So you can understand what is the beauty. So because no scattering, no loss, so basically lifetime of device is increased. So that's why these materials are very interesting for the device application point of view in the future. So now question is that how we can understand these materials. Uh, if we remember, through the through this solid state physics, through the band diagram, whenever we have any material, so we have like two type bands. One is conduction band, and second one is the valence band, and in between we have gap. So through this gap, we can decide material is metal, semiconductor, or insulator. So, but this two-dimensional material or topological quantum material is totally different than these materials. I will explain in the last after explaining some fundamental property. So now, if whenever we would like to understand two-dimensional material or quantum materials very specifically in 2D materials, it's necessary to understand the behavior of the quantum Hall effect. So basically, this one is starting from the Hall effect. So whenever we have any material, So just assume here we have one material, current is flowing along the x-axis and a magnetic field applied along the z direction. So because current is flowing in this direction, so what possibility we have? And a magnetic field applied along the g-axis. Then one voltage developed perpendicular to this electric field and a magnetic field. That voltage is known as the Hall voltage. Okay, so basically this is the basic concept of the Hall effect, which one is developed by Edwin Hall in 1789. So basically what happened here? So okay, so let's understand that when if because what we are getting here, current is flowing in this direction, okay, and magnetic field applied along the along the g direction. So one Lorentz force develop here. The Lorentz force, that one is F equal to Q V cross B. We can easily write that expression, and this so, because it totally depending, like we have electrons or hole. So, if we have electron, suppose electron is moving, our charge is negative, then according to because Lorentz force is developed, so charge is going to accumulate on one surface. Negative charge is going to accumulate on one surface. With respect to one surface, other surface will be positive. So that's why this Hall voltage develop here. So we can easily understand this Hall effect at equilibrium condition. So this is Lorentz force, that one is F equal to minus Q QE plus QVB. So in equilibrium condition, these two forces are equal. Magnetic force equal to electric force. These two are equal. And here E is the charge of the electron. H is the basically this electric field, and VD the dip velocity, which one is generating due to electric field and magnetic field, and BZ is the applied magnetic field along the g-axis. And because current is flowing along the x-axis, so we can easily write the expression, because if you look, current is flowing along this direction. This is the cross-sectional area A. So we can easily write Ix, which one is flowing along the x-axis, that one is equal to minus Ne VdA. Or Ix equal to, we can replace this dip velocity using this expression. So we will get Eh by Bz multiplied by A. Then current density, basically that equal to Ne Eh by Bz. And electric field have relation with the voltage. So Eh, if you look here, this voltage is developing between these two. So if this length is L, so we can easily write Eh equal to Vh by L. So just replace this Eh by Vh by L. So we will get the expression Vh equal to minus Ib Net. Or in place of 1 by Ne, we can write RH, that one is the Hall coefficient. Hall coefficient RH equal to 1 minus 1 upon Ne. Now, so we can easily plot the curve between VH, VH versus B, keeping the current constants. Then we will get the slope. So you can easily, this is the slope we will get. So through this slope, if this slope is positive or negative, accordingly you can decide your material or any material is N type or P type. This is the very unique, Hall effect is very unique setups using that people are measuring the types of charge carrier. You can also measure the mobility. You can you can also measure the conductivity. These all you can easily measure. But this, this behavior, linear behavior, will get only the low temperature. Now, if we reduce, because this diagram, if you look here, this is the width, this is the D. This is the D means the thickness of the material. So if you start to reduce the thickness of the material, okay. So suppose if you are mobile, and if you start to reduce the thickness of the this your mobile, then what you will find? So material will convert from 3D to 2D. If material is converting from 3D to 2D, so it means whenever current is going to flow through this material, so this current is going to flow only on the surface of the material. So here uh, we can measure two types of voltage. One voltage uh, direction of the current. Basically, the okay between these two contacts. Okay, you can say the Vx axis. One voltage we can measure between these two contacts, which one is perpendicular to this current. If magnetic field is applied here, of course, we can say that perpendicular to a current and a magnetic field. So basically in this direction. So here we can measure two types of voltage. One is Vx axis and a V R, or okay, you can say the Vxy, or you can say the transverse voltage. And if material is two-dimensional material, so you will easily get the interesting property like Professor Kirchin got. Normally, any two-dimensional material shows this behavior. So this is the transverse resistance. Transverse resistance or you can transverse resistance equal to V R by Ix. Ix is the current which was flowing along the x-axis. Vy, this is the Hall voltage or perpendicular voltage uh, with respect to current and the magnetic field. So what they got, if you see, initially this one is almost linear, and after then if you see step type phenomena started to come. And same times if you look here, initially almost no change, then some oscillation start, then if you see this oscillation intensity started to increase. So basically, this one is also resistance. This one is also resistance. This axis showing the resistance. This one is the magnetic field. Of course, they have performed this experiment at very low temperature. So if you look this data carefully, you have two types phenomena. One, you are getting step type behavior. So when Professor Kirchner analyzed, he got this Rxy equal to h upon I square and I equal to 1, 2, 3. So it depending like 4, 5, 6. Similarly, if you go in higher field, then you will get I equal to 3, I equal to 2, I equal to 1. So if I equal to 1, so h upon E square. So Planck constant value is known, this electric charge is known. So if you calculate this value, you will get around 28 kilo ohm, 25.8 kilo ohm. So this is the standard resistance if you measure the sample here and there. Same times you are what you are getting. Whenever you have step type phenomena, then if you look here, material is showing almost resistance is zero. And when you have jump, then you are getting very large resistance. So if you look like this is a very interesting phenomena, it's indicating that material is showing insulating and metallic type nature. But resistance is zero means what? Metallic nature and resistance is very large means insulating. So same material, so the two type phenomena. One is okay, you can say the metallic nature. Second one is the insulating nature. Now question is that how we can understand these phenomena in quantum materials, two-dimensional quantum materials. So of course, this phenomena we can easily understand taking account the basic concept of the magnetism through classically as well as quantum mechanically in or simply you can say the magnetism in the quantum material. Before moving the this quantum phenomena, so just try to look how dimensionality affect the property. This is a very interesting point because we are going to move from 3D to 2D material. So this is a very good aspect to understand here. Just try to look. We know that electric field equal to rho resistivity multiplied by the current density. And this rho is basically tensor quantity. And because here, if you look here, this material, whenever current is flowing along the x-axis, the two type electric field is generating. One is along the x-axis, second one along the y-axis. Okay, so we can easily measure these two electric field or voltage, as you can say that. So because this rho resistivity is the tensor quantity, you can easily write rho xx, rho xy, and the rho these two components are antisymmetric. Basically, this perpendicular component is always antisymmetric. So rho xx, rho xy minus rho xy, rho xx. And try to look here because current is flowing only along the z-axis, along the x-axis. So it means y component current is 0. So we can easily write gx 0. So Ex equal to rho xx jx and Ey equal to minus rho xx jx. Now, from using these two equations, we can easily write resistivity rho xx equal to Ex by gx, and same times we can write, we can calculate the resistance of resistance equal to, we are knowing that like Vx by Ix, voltage per direction of the current divided by current. ELX, electric field generated, direction of the current, and JXA. So rho x basically L by A. So dimensional quantity is coming here. If you see rho x basically is depending with the dimension. Resistance and resistivity have at least this dimensionality component. Similarly, if you look this rho xy, basically Hall resistivity, or okay, you can say the um, resistivity which are developing perpendicular to current and the magnetic field along the y direction. So basically rho xy equal to minus Ex by Jy. So rho xy equal to minus Vy by Ix minus Ey uh, width divided by Jxa. So basically if you measure the in three-dimensional material, if you measure the resistance or resistivity, both are different because dimensionality component is there. Only I used to say this point here. So resistance and resistivity is not exactly same in 3D material. Just remember this. And through this cylinder, people have analyzed that this resistance and resistivity have relation, something like that, rho equal to resistance equal to rho L ke power 2 minus D. So, so how this one is correct? Let's see in 2D material also. Whenever we are talking about the 2D material, so definitely thickness is not there. Okay, so only we have weight and the length of the material, and the current is flowing along the this direction. Okay, now you have to calculate rho xx, Vx by Ix, Exl by Jxw, rho xx, L by W. And if you calculate this rho xy, because thickness is not here, so minus Vy by Ix minus Ey width divided by Jx width rho xy. So just this is the beauty of the 2D material. Here resistance, this Hall resistance and resistivity is exactly same. This is the beauty of the 2D material. So always remember that in two-dimensional material, resistance and resistivity is exactly same. But in 3D material, sorry, Hall resistance and Hall resistivity, remember that. But resistance, means longitudinal resistance, definitely have dimensional parameter, but Hall resistivity and resistance is exactly same in 2D material. This is the one aspect. The dimension affect a lot whenever you are going to perform the Hall resistance. This is the major reason. Uh, a major reason whenever you are performing the Hall effect measurement, then be careful about that. Okay, so maybe whenever you are saying that in 3D, very thick sample, when you are measuring the Hall effect, maybe some dimensional component is there. So this Hall resistance is not Hall resistance. Some other longitudinal resistance component is also there. So it's always affect. Maybe data will not correct. Just remember that. And same times, if you remember the density of states, so I hope you even remember that. I will not go in that much detail. So if you talk about the 3D material, density of state is proportional to e to the power half. Okay, and one dimensional material density of state is proportional to e to the power minus half. But if you remember, in 2D material density of state is not depending on the energy. It means one energy state is not affected by other energy state. All are totally separated. So this is here like at least 2 points which are very useful whenever you are going to explain the property of two-dimensional material or quantum material. Okay, so now try to remember, like, because whenever you are measuring the Hall effect measurement, what we are doing. So, okay, before moving on, this is remember that classical Hall effect and quantum Hall effect, these two are different. So, classical Hall effect means whenever we are measuring the Hall effect at very low field. Normally, okay, you can say you up to 2 Tesla, not more than that. So, you will get almost linear behavior. But whenever you are going to measure the Hall effect, very high magnetic field, that and specifically in two-dimensional material, then so you will get the quantum phenomena. So quantum Hall effect basically you will get very high field, not lower field and a low temperature. So always remember that. Now we are going to understand because what we are doing in Hall effect. Whenever we are measuring the Hall effect, we are doing two things. One, current is flowing along the x-axis and magnetic field applied along the g-axis. Okay. Then one voltage developing perpendicular to this current in the magnetic field. So now we can choose like two different conditions and understand exactly how electron is behaving in these quantum materials. Try to look the case one. What we are assuming equal to 0 and magnetic field is not 0. What this applied magnetic field is not equal to 0 but equal to 0. So if you remember, if you have any material, if you are not applying the electric field, so definitely you can say that electron is not moving in the material. Okay. So it means energy is constant. When E equal to 0, it means energy is constant because power delivered that will be 0. Okay, with Lorentz force multiplied by a dot product with the velocity that is equal to 0. It means what? If you just take the mv dot v dy dt half mv square equal to this Lorentz force multiplied by velocity, that will equal to 0. It means half mv square equal to constant. That's what I'm saying. Like whenever E equal to 0, electron is not moving. Okay, it means energy is constant. Energy is constant due to basically because of power delivered that will be 0. Okay, it means that this velocity, because electron is moving after applying the magnetic field, this velocity have two components. One, perpendicular component, and second one is the polar component. Because magnetic field applied along the g-axis, so you have two possibility of the movement of the electron along the x-axis or along the along the y-axis. You have two possibility. Because electric field is 0, so it means definitely we can say that V perpendicular is almost constant. It's not changing. V is not changing. The electric field is not 0, so V is not changing in direction of current. So we can say that. So now we can easily write perpendicular equation of motion. Of course, we have several other component of that because time is not permitting, so I'm not going on those details. So we can easily write equation of motion on these two directions along the x-axis and along the y-axis. So mvx dot equal to qvyv. Similarly, mvy dot equal to minus qvxv. So we will get these two equations are these two different motion, one along the direction of current, one along the y-axis. If we take if we differentiate equation 1 and 2 with respect to time, so what we will get? Just try to look. We will get mvx double dot equal to minus omega v square vx. So what this one indicating? So this one is indicating that so after applying the magnetic field, this electron will start to move, do the harmonic, behave as a harmonic oscillator with cyclotron frequency omega p. That one is equal to qb by m, and it start to move in the circular motion with the cyclotron frequency. Okay, so because this is a second order differential equation with respect to velocity, so we can easily calculate after solving the second order differential equation, we can easily get the Vx, that one is equal to V perpendicular cos omega b t. Similarly, we can calculate using this equation too, we can calculate Vy also, that one is V perpendicular sin omega b t. Okay, and if you integrate with respect to t, then we can easily get x equal to x0 plus v perpendicular omega b sine omega bt and y equal to y0 plus v perpendicular omega b cos omega bt. So what we are finding from here? We are finding that this electron is moving. Electron orbiting in this orbit of charge particle about the guiding center x0 y0. And if we have positive charge, we'll get it's going to move on this direction. If in negative charge, it's going to move in this direction. Okay, so that's what happening whenever E equal to 0 we have. Now take the case second, whenever E not equal to 0 or B not equal to 0 and E is perpendicular to, just remember that magnetic field applied perpendicular to direction of current or direction of the electric field along the x-axis. So if we can write the force, that one equal to QE plus V cross B. And if you remember in the first case, when E equal to 0, V perpendicular parallel was constant. But when we electric field is not 0, then this parallel velocity is not 0. That one is also changing. That one is equal to QE perpendicular by M. So it means that now only difference, what difference we have? When E equal to 0, B not equal to 0, this charge particle are orbiting about this guiding center x0, y0. Of course, direction is depending types of charge carrier. If positive charge is going to move in the clockwise, if negative charge is going to move in the anti-clockwise. But whenever E not equal to 0, this guiding center x00 moves perpendicular to the both E and B. So it's going to form the uh, path something like with one drift velocity. With one drift velocity. Okay, so now we are going to understand because this is the classical phenomena. Up to now, what I discussed, this is the totally classical phenomena of charge particle in magnetic field in quantum material. Now, try to look whenever we have like two-dimensional material and magnetic field applied perpendicular to this plane. So, through this classical phenomena, what we call all electrons or charge will start to move in this circular motion with cyclotron frequency, cyclotron frequency QB by M or EB by M, whatever you can say. Okay, so it start to move in the circular orbit. So it means like, see, whenever we have a material, we have n numbers of atom within that. So it means we have n numbers of electron. So whatever electron we have here, they are going to move here in circular orbit in circular frequency. This will going to move here. This one going to move here and this here. But one major difference, just assume if you have some electron here, okay, some nucleus are here. Is it possible this electron will complete the path? No. This electron will not complete the path. So whatever electrons we have near to edges, they are not going to complete the path. So this edge or this edge. So it means they are going to skip the orbit, are going to make the path something like they skip the path. So they form the channel on these edges. Similarly, they form the channel on other edges in opposite direction. So try to look here. Here we are finding two things. whenever magnetic field applied in two dimensions perpendicular to plane, then electron which are in center, they are moving in a circular orbit with cyclotron frequency omega b equal to eb by m, and it's fully depending on the magnetic field. So, but what if an electron near to these edges, they are not able to complete the path, they are going to skip the path, so they are going to move something, they are form the channel. So current is going to move on this edge and this direction. Similarly, this edge are in opposite direction. So that's what happening in two dimensions. And the same times in this region, if you look here, no current is flowing in this direction. So basically, we are getting some idea. If you remember, I have already shown one data where Hall resistance were quantized and Lagrangian resistance was some places zero and some places maximum. So that analysis we are getting from this picture. Now, so okay, so now we are going to understand exactly what happening in such type material. So through the Schrodinger equation, this is the well-known Schrodinger equation. This is the well-known Schrodinger equation. As we know that minus h class square by 2m del square plus potential psi equal to E psi r. This is the well-known Schrodinger equation. E is the total energy of the system. Okay. So, because between the boundary, electrons move the freely. So it means because we are assuming electron move as a freely within the two boundary, so we can assume potentially almost zero within that. So we are assuming potentially zero. So now h class square by 2 of del square psi equal to E psi r. So this equation also you can write in form of momentum p square by 2m psi r E psi r. So now question is that this equation is valid only whenever no magnetic field is applied. Just remember that. If we are applying the magnetic field, then this momentum will change from p to minus p minus qa. Okay. So now momentum will change from p to minus qa. So, because we are applying the uniform magnetic field perpendicular to this plane along the g-axis, okay, this magnetic field is uniform along the g-axis, but within the plane, this magnetic field is this within the magnetic field, within the plane, we are going to look the magnetic field using this expression B equal to del cross A. Okay, because magnetic field along the g direction, it's uniform, but this vector potential A is the magnetic vector potential, which one is not uniform. This is the very interesting phenomena. Magnetic field is uniform, but vector potential is not uniform. And because this A have two directions, one along the x-axis and the second one the y direction. Or it's also your third possibility that one may be between along the x and y both directions. So that's why here we have three possibility. We can write this A in form of B on three way. A equal to minus B by 0, 0, or A equal to 0 Bx 0, or A equal to by 2 minus Bx by 2 equal to 0. So we have three combination. So if you use any one of the combination, you will get exactly same result. It's not going to change symbol. So this one is known as the basically gauge field. This one is known as the gauge field. It's given by the gauge phenomena to solve such type problem. So using the gauge theory, we can easily solve this quantum phenomena property in two-dimensional material. Now, try to uh, take this first one. Just take anyone. If you choose anyone, you can solve the problems and you will get similar results. It's not going to affect. Now, so in place of P, we are going to write. So because what we are assuming, we are going to choose like this first component. So we will replace, because P have three component x, y, g. So we can rewrite px square by 2m, p square y by 2m plus pz square by 2m. So px we can replace with px minus eby whole square plus py square by 2m plus pz square by 2m psi r er. So now, because magnetic field applied along the g-axis, it means along the g-axis, electron have free motion. Electron have free motion. So it means we have idea about solution along the this g direction. Okay, so this solution is exactly similar to free electron problem, free electron potential problem. So anyone who have already some have basic idea about the quantum mechanics of free electron problem, so they have idea if electron is really moving, then what type solution you will get, that one is well. So it means we are not going to talk about that. We are going to discuss only these two components. Px minus Eby whole square by 2m plus Py square by 2m psi r equal to E psi. Now try to look here, because here we don't have any y component, but here we have not x component, but we have y component. So it means that px uh, px is conjugate. Okay, this commute with the Hamiltonian. Hamiltonian means total energy of the system. This momentum along the x-axis commute with the Hamiltonian. That one is always equal to 0. So it means this px we can easily write equal to h cross k. Okay, so basically this one is coming exactly from the free electron problem, where px equal to h cross k and k equal to 2 pi nx by lx. Lx is the dimension of the length of the potential. Okay, length of the potential. And nx equal to 0, 1, 2, 3, 4, something like that. So basically it's quantized. It's quantized. But along the y-axis is not commute, so basically it's equal to IH cross, because here you have y term. So if x term, then definitely like this px will not commute. But here y you have, so that's why this y will not commute. Only this px will commute with the Hamiltonian, and this will always constant or conjugate equal to h cross k, and k is the wave vector that will equal to 2 pi nx by lx using the boundary condition in electron problem, where nx equal to 0, 1, 2, 3 something. Okay, just move further. So now, just try to what we are going to. So in place of px, we have to write h cross k minus eby whole square by 2m plus py square by 2m psi r e psi r. So now try to rearrange. Now only we are going to rearrange this component. Try to rearrange that. So we have to write py square by 2m plus half m eb by m in bracket h cross k eb minus y whole square. So this one is exactly same, only just after rearranging that. Psi r e psi r. Okay. So here py square by 2m plus 1 by m eb by m y. Just we are taking y first, h cross k eb, because square, so it's not going to affect. So y minus h cross k eb whole square. Okay, so this value normally people used to write in form of lb. Lb is the basically magnetic length. Okay, lb is the known as the magnetic length. So now, okay, we have to return this expression. This expression is exactly similar to harmonic oscillator expression. This well-known expression in the quantum mechanics. So this is the exactly similar to harmonic oscillator. So once we got the idea, this problem is exactly the type like the harmonic oscillator. No reason to solve further. Just you can take the direct solution of those expressions. Okay. So it means Energy we can easily write n plus half h cross omega c, where omega is nothing, this is cyclotron frequency, eb by m. So we can take differently here. N is you can start from 0, 1, 2, 3, 4, something like that. So just if you plot this 1, 2, 3, 4, then what you are finding? E versus K graph, energy versus wave vector plot. So you can see here, we are easily finding, we are getting the energy levels which are equally spaced. These energy levels are known as Landau energy levels, name of the scientist who discovered this. Okay, and if you are interested to write the wave function, so you can write, that is not a big issue. Wave function, that one is equal, that one have basically three component, x component, y component, and a g component. So x component, if you write the wave function, that one is e to the power ikx, e to the power ikx, and then an e to the power minus eb y minus y0 whole square by h cross, then Hermite polynomial eb bracket y minus y0 h cross. So on that way you can write the wave function and energy expression for this charged particle in uniform magnetic field. These Landau labels are highly degenerate because these Landau, it not here it's looking like they are single energy levels, but these Landau levels are highly degenerate. Why? If you look here, uh, this LB equal to H cross K by EB. Okay, LB, this magnetic length dot, if we are getting that only inversely proportional to magnetic field, and the K term is here. K is nothing. K equal to, basically we have K equal to 2 pi nx by Lx. Okay, so just if you put the value H cross 2 pi nx by EB Lx, that's what you will get. And if we assume maximum degeneracy of the length, so just see, whenever we are saying if you move from here to here, or if you move from here to here, so basically this is the LB, this is the LB. So if you move from here to here, so definitely like this length is also fixed. After certain time, you will reach on the maximum length. After that, it's not possible to move. So that maximum length, if we can say this is the Ly, okay, Ly or Ly, then degeneracy, that one equal to, basically you will get EB Lx Ly. If this one is Ly, so EB Lx Ly upon 2 pi h cross. Or if you rearrange that, EB Lx Ly, basically this is the area of the sample. So A by 2 pi h cross, then BA by H, okay, H by E. So if you H by E is again one constant. This one is also known as the flux quanta, which one is flowing through the material. H by E is the flux quanta. BA, again, if you look, this is the phi. If you remember 10 plus 2 physics, BA is nothing, this is the change in the flux. Okay, so basically this one is the phi by phi 0. Okay, so that's what. And this degeneracy is totally depending, coming due to this kx. So it's indicating that the Landau levels are highly degenerate. Now next question, what about the group velocity? Because these Landau levels are totally flat. So if you calculate the group velocity Vk, that one is equal to 1 by h cross del E del y equal to 0. So this one indicating that this Vk is 0 because Landau levels are flat. So kinetic energy is 0. Okay. So only what we have, only remaining is the potential energy. So when we are talking about the charged particle in uniform magnetic field, when electric field is 0, then only we have, only and only we have the potential energy. Okay. So now next, if you move that, So when we are talking about the rho xx or rho xy, hard resistivity, rho h equal to h upon I e square. If you look here, rho xy equal to h upon I square. So what about the I? How this I term is coming? Question is that. So I is nothing. That one is equal to basically n0 charge carrier concentration divided by G by A. D is AC divided by the area. Or n0 divided by EB by H. Or n0 divided by B by H by E. Or n0 phi 0 or B. Basically phi 0, if you calculate H by E, you will get 4.13 cross 10 power minus 50 Weber. So if area is not involved, then you can also write on this. So basically, what we are getting from here, we are getting two types of concept here. Whenever this uh, through the edges, we are getting the conduction due to skipping of the orbits, and in the center, material showing the insulating nature. So these data we can easily explain on the basis of, at least primarily we can easily understand this property, or we can easily explain this property taking account this phenomena. Okay, so one more point: if you have if group this group velocity is zero, what about the current density? If you calculate that, then definitely you will find that one is also zero. Okay. Now, up to now, what I discussed, electric field is zero and magnetic field is not zero. Okay. Now, if electric field is not zero and magnetic field is not zero, then what happens? So, definitely, whenever we are going to write the Hamiltonian, we will get the additional term, that one is EEX. Okay. So basically, and if you write the energy, so you will get additional torque n plus half h cross omega p minus EB KLB square plus EB by m omega p square plus half m E square B square. So basically, this is what this electric field is playing the role. Basically, this one is confining the potential, pushes up and down levels at the edge of the sample. So what happening? Whenever charge particle is coming from here to here, this electric potential is creating the slope here. So that one is means is creating as a potential. So it means electron is going to move uh, between only here to here. Okay. So on that way, using like this concept, we can easily understand that how we can explain this quantum Hall resistance and quantum Hall effect phenomena in the two-dimensional material. So basically, if you look this is the basic explanation of the this quantum Hall effect data or quantized Hall resistance data. So if you look here, so whatever electron you have edges, they are just skipping the orbit, so they are forming the conducting channel on this direction, in opposite direction, in opposite direction. So and in center, whatever electron they are just moving in the orbit with cyclotron frequency. Okay, so in this region, almost no current is flowing, so we can assume material is behaving as insulator, and through these edges, materials behave as a conducting nature. So this is the first point. Second, when you are increasing the magnetic field, then cyclotron frequency also increases, and it's going to affect the radius. So up to very high magnetic fields, some electron which are orbiting here, they got sufficient amount of energy, sufficient of radius, they reach up to boundary. So they are going to jump from here to here. So that's why you are used to get jump in the Hall resistance data. Whenever electron is going to jump from uh, center to the edges, then you will get the step in the Hall resistance data, and similarly change in the resistance, change in the longitudinal resistance whenever electron is going to move from center to the edges. So this is the basic way, this is the fundamentally, you can easily understand how this magnetism in the Hall effect phenomena in two-dimensional material. So I think time is almost completed. So Manojji, hello, hello, Manojji,
Yes, sir.
हम अभी क्या करना है बताइए.
Sir, we can take some questions. अभी कुछ questions हैं.
Okay, okay, okay.
So
Yes,
yeah,
yes, yes.
करना चाहते हैं तो we can continue that.
I think 5 minutes is not sufficient. I better I take the questions.
And that's fine. Yeah, we can take the questions. There are some questions in the chat box.
Yes, yes. So what?
From Mr. Russia, can we apply a magnetic field that can destroy the JZ and JS and
Uh, can apply the magnetic field that can destroy the current density along the J direction. Yes, and JS. No, and this okay. So whenever we are talking about the current density, basically we have current is moving only along the x-axis. Just remember that current is moving only along the uh, x direction. J direction current is itself zero. So what is the JS here? Just I want to know that. What I am not able to understand
Rahulji, if you're there, probably you can type in the chat box again what does this JS mean, so that we can answer the question.
because in quantum Hall effect phenomena, here we are not talking about the JZ or JX. JX is the only jet. We are talking about the JX. Y is the zero. This is the current density. This is not total angular momentum. Just remember that.
What Mr. Rajesh is saying is that it's spin and Bohr angular momentum.
No, 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 no. Here basically JX we are talking about the current density. This is the not total angular momentum.
Yeah.
This is a little bit different. JX is the current density basically. Okay, so next question. What is difference between 3 and 4 slide? 3 and 4.
This need to be clarified which slide they are talking about.
Let me see.
Devanshu, if you can clear about which slide you were referring to. This is from the
3
first
and
lecture.
they are asking about first lecture.
Yeah, because this is at 3:27, so this will be from the first lecture.
Okay, okay, okay. Let me open that. Okay, okay, okay. Three. Okay. I think this PPT is visible, na?
Yes, it's
Yes.
visible.
Yeah. Okay. If you look the three basically just I talk about the application. After that, I started the explanation of the origin of the magnetism in the materials. Nothing else. Of course, these two slides are totally different. Here, this is just application. If you look the credit card, of course, this one is magnetic wave system. If you look the hard disk, this one is also magnetic wave system. If you look this our electric power generation through this uh,
Wind.
uh, through this, that one is also basically based on the magnetic origin, magnetic material. Okay, so let's move next question. Okay, okay, adiabatic region. Okay, so adiabatic means like I hope if you can understand understand by thermodynamics, adiabatic means what? we have something in the closed environment. And if you remember the adiabatic concept, we are not going to take any amount of energy from the system, or we are not going to provide any amount of energy to the system. So that one is totally separated from the surroundings. So if anything happening within the system. So that's why total entropy of system is always constant. This is the major if he is able to understand, it's okay. Otherwise, I can open the slide and then explain again.
Maybe you
Oh,
can type in the chat
Mahesh
box.
ji, Mahesh ji, are you here?
Probably Mahesh ji can type in the chat box if that is fine, or whether the sir needs to open the slide. By that time, probably we can take question. Mahesh ji is requesting to explain it from the slides.
Uh, Ranjan. Some person asked by Ranjan Kumar. Yes, whenever you are applying the magnetic field, so entropy always reduce because what we are doing, a random system always have more entropy than a line. This is the basic concept. Then next, okay, what magnetic materials are used in the electric motor and generator? I think this is the very basic questions you can find. Uh, because these days things are very advanced, so maybe they have changed a lot. So you can find this one. It's not very. I am coming on next. 2D material classified based on geometry or electron orientation. Okay, so 2D material, of course, like depending on of course, geometry is the first parameter, of course, because reason is very simple. Whenever we have 2D material, so density of state is also proportional to e k power 0. Means it not depending on the energy. One state is not affected by other state. This is the first point. Same time, whenever reducing the dimension or we have 2D material, then Hall resistance and resistivity is exactly same. So definitely, it's more dimensional, depending on the dimension, not geometry. I am not talking about geometry. I am talking about the dimension. Geometry is totally different because if we have 2D material, we can make through the patterning different shape, different geometry. That one is possible. So basically, here I am talking about dimensionality, not geometry. In I think it's okay if anyone have additional question, then maybe I can explain.
There is a question from Mr. Suresh Kumar. How is it affecting the effective mass of the electron in semiconductors?
Okay, so I think it totally band dependent. If you remember the effective mass of the electron inside the material, m star equal to h class square by d square e by dk square. Second derivative of the energy with respect to k. So it totally band dependent. Okay, so effective and if you look the silicon or germanium in each one, you can easily calculate the effective mass. So that is not a big issue. You can calculate the effective mass and you will get the different than the free mass of the electron.
And Mr. Amit is asking to confirm the quantum behavior of a material, what magnetic characterization technique may be used?
Okay, so magnetic characterization techniques. So yeah, I think you have you can understand several ways. So one, okay. So you can use the like this through the magnetization. You will get the idea about this quantization effect. Because when you are talking about the quantum material, so two-dimensional material is one part. Similarly, if you remember the superconductor, they are also so the quantum behavior. So differently using the magnetic property, using the transport property, because if you have 2D material, you will get the localized and unlocalized state. So several concepts you can understand through the transport. Several concepts you can understand through the this uh, magnetic. But major, whenever we're talking about topological quantum material, you will get the basic understanding using the RPS measurement only. RPS measurement only. Because then only you will get a dispersion relation. Because when you talk about two-dimensional material, what is the beauty? If you look the whole picture, then you will find these all materials have linear dispersion relation. Linear means like this, so the Dirac cone type behavior. Dirac cone means like if you have linear behavior, effective mass like this pi by d, if you calculate that, you will get the G. So basically, uh, you can say that like uh, majorly like you will get the if you are interested to understand कि your material have this topological quantum property or not. First measurement definitely people want to purpose measurement. Second, of course, you can go several other transport through the magnetic. Depending, you have to go at lower temperature. Then only you will get this quantum state phenomena.
Okay. There's one more, probably the last one we can. Bhavna Mahesh, yes, he was asking what the adiabatic regions is requesting to explain it from the slides.
Okay, so let me open again. Okay, this one is visible.
Yes, it's visible.
Yeah. So, uh, okay. So to understand the adiabatic, what we are doing. So you just assume you have applied the magnetic field. Okay, and one way you are doing everything in the open atmosphere. So whenever you are doing anything in open atmosphere, so process is known as isothermal process. Okay, and now suppose if you are doing same process in the closed system where you are neither you are giving any amount of energy, neither you are taking any amount of energy. So if you are reducing the magnetic field or applying the magnetic field, so if you are doing anything, suppose you have some magnetic material and you have put some, in closed environment where heat is neither coming out and the heat is neither coming to sample. So in those cases, total entropy of system is always constant. So this is the major difference. In adiabatic region, total entropy of system is always constant. But isothermal entropy change, in isothermal process, total entropy of system will never constant. Sorry, entropy change. But here, total energy of system is always constant. Entropy is always constant. Anything else?
No, sir. There is one more last question, possibly. Please explain the typical characteristics of two-dimensional materials.
Okay. So whenever you have two-dimensional material, okay, so definitely first part they have to look uh, just it totally depending on the facility. First part definitely you have to go one you can measure the RPS measurement. Okay, so if you do the RPS measurement, then you will see the Dirac type cone type structure in between the conduction and valence band. Basically, because electron is moving, electron. Let me turn on the video. Yeah. So basically, electron move through the edges. Okay, so these channels basically almost on the linear dispersal relation. So that you can easily see in the RPAS measurement. So first measurement is the RPAS. Okay, so second, whenever you are going to perform this Hall resistance and Hall resistivity at lower temperature and high magnetic field, then you will get this quantum phenomena. Third, you will get the localized effect in the resistance in MR measurement also. Means if you remember, if you measure the MR, basically it's going to move in the parabolic shape, and with increasing temperature it's going to change the shape. So using the MR measurement also you can get several behavior up to dimensional material, several effective property up to dimensional material. Fourth, uh, fourth was of course like about the effective mass. Effective mass are these mobility, these are very high. If mobility, uh, these are materials are well known for high mobility. Okay, and fourth, even if you do the theoretical calculation, then you will find this density of state is not depending on the energy. So these are the few things using that you can directly get the idea your material is 2D or not. And one more point, whenever you are performing the most important point,
Thank you, sir.
whenever you are
There are a
going
lot of
to
questions and you
measure,
explained each one.
when you are going to measure Hall resistance and Hall resistivity, both exactly you will get the same in 2D material. I think that's all.
Yes. For I hope whatever you were. There was a question which actually tells part is really very interested in the talk. So thank you so much, sir. And again, Manoj ji, and personally, I would like to thank you that at a very short notice you just said yes to us, because we know that just 3 days back we sent an email to you and you said that you are okay with the talk.
I know that it was tough for me
So
also.
thank you so much, sir, for that.
So, so anyway, thank you. If slide is required, then I will send in the mail. Then maybe you can share with participant. Hello, hello.
Yes, sir. Thank you, sir, for the session.
Yes,
And we
sir.
will
You
mail
can.
you
Yeah, no,
regarding the. Yes, sir. We
just I
will
am asking
probably.
if slide is required, then I will send in the mail.
Yes, sir. Thank you, sir. We will mail you regarding the PPT also. Then you can send in the corresponding
No, I am
screenshot.
going to send right now.
Yeah. Okay, sir. Thank you, sir.
Okay, okay.
Okay, sir. You can send it right now also.
Okay,
No
thank you.
problem.
Thank you very much.
Thank you so much. हाँ, हो गई 1 मिनट बस हो गए आ जाओ